Here's an introduction to experiment 14, intermolecular forces. So here we're looking at the comparison of intermolecular forces between different types of molecules. So identifying which molecules have London dispersion, dipole-dipole, and hydrogen bonding. And then looking at their evaporation rate in order to see and compare their intermolecular forces. The procedure is shown in the video. So here for the pre-lab, you'll complete this whole page. You'll add up the molar mass for each compound, and you'll list the intermolecular forces. So for example, if we look at methanol here, we know that all molecules have London dispersion forces. This one also has a center atom carbon, and the four surrounding atoms are not identical. Therefore, it is a polar molecule. So that means it also has dipole-dipole forces. And then it also has an oxygen directly attached to a hydrogen, which is the one criteria for hydrogen bonding. So he also has hydrogen bonding. So for each of these molecules, you'll go through and list which intermolecular forces are present. These up here, just to kind of classify them for you because the lab will refer to them. The ones that end in the ending OL are called alcohols. And you'll notice that they all are similar to one another because they all have this OH group. And the OH group, like we already saw, gives them all hydrogen bonding capabilities. So you'll notice that about alcohols. The second group are these two that end in the ending -one. These are called ketones. If you look at their structure, they don't have hydrogen bonding because their O is not directly attached to an H. However, they are polar because if you think about this carbon right here as their center atom, they have a carbon, and then an oxygen, so they don't have the same surrounding atoms, which means that they are polar. So these are going to have London dispersion forces, and they're also going to have dipole-dipole forces. And then the last group down here ends in the ending -ane. These are called alkanes. And if you look at them, they only have C's and H's, which carbons and hydrogens have very similar electronegativities. So these are nonpolar. Therefore, they're only going to have London dispersion. So now, whenever the lab refers to alkanes or ketones or alcohols, you'll have an idea who they're referring to. You'll complete all of the pre-lab, but here I'll focus on number 3 because it kind of is the whole understanding of the lab, is if we think about evaporation and a substance's intermolecular forces, what we know is that the higher the intermolecular forces between substances, then the lower the evaporation rate. Because the molecules are more attracted to one another. So if they're really attracted to each other, such as hydrogen bonding, then they're not going to evaporate very readily because they are attracted to one another. And the way we're measuring this in this lab is looking at a change in temperature as it evaporates. So what we can also say here is you also have a small change in temperature. So small delta T, a small change in temperature means very little evaporation rate, and very little evaporation indicates greater intermolecular forces. And so you'll complete the pre-lab. Here's your data sheet. So in the video, a few have been demoed. So 2-propanol was demoed in the video. And then methanol and acetone. So you'll have graphs that you'll be reading, and you'll get the maximum temperature and the minimum temperature. And using those two, you'll calculate the change in temp. So the rest of the points, the rest of these temperatures will be given in the data. So the starred ones you'll find in the video, and all of the rest will be given in the data and the info handout. Okay, so you can find those and therefore calculate the delta T. You'll answer the post-lab questions using your data and your understanding of intermolecular forces. Down here in number 5, what you're going to be doing is comparing two atoms or molecules and their intermolecular forces, and you're circling the one that has the lower melting point. So I'll do one example with you here. For example, HCl, if we think about HCl, we know that he's going to have London dispersion forces. He's also two different atoms attached, which means he's going to be polar. So he's going to have dipole-dipole. He's not going to have hydrogen bonding because the hydrogen is not attached to an F, O, or N. So he just has London dispersion and dipole. If we think about carbon, we have to know the primary bonding forces that exist as well, such as metallic and covalent network. And here carbon is one of those that falls under the covalent network. So the carbon has covalent network, which is a primary bonding force and much, much stronger than anything else, than any of the intermolecular forces. And so here what we can say is we know that carbon automatically has higher melting or boiling point because he has one of the primary bonding forces, which is ionic, covalent, or metallic. So we would circle HCl, and our explanation might be that carbon has covalent network, which is a primary bonding force. And you'll continue that through as you compare these different atoms and molecules. And then lastly, you'll get to this number 6, and the instructions are up here. What I want you to do is actually look up the boiling points. So you can Google, look these up. So you'll look up the boiling point for these different substances. You'll calculate the molar mass using the periodic table. You'll list the intermolecular forces that are in them. And then you'll just rank them looking at what their order is. So anything with a primary bonding force is going to be higher than anything that doesn't. And then you'll compare from there on the London dispersion, dipole-dipole, and hydrogen bonding. Here I'll review that really quickly down here, where primary bonding forces include ionic bonding, so you're looking for a metal and a nonmetal. Covalent network, which you're looking for carbon or silicon. Ionic, an example would be NaCl. And then lastly, metallic, which you're looking for any metal that's all by itself, silver, iron, etc. Those are all way stronger than the normal intermolecular forces. And remember, of the intermolecular forces, hydrogen bonding is the strongest. Next would be dipole. And then the weakest are your London dispersion forces. So that'll just help you kind of, as you go through the lab, having an idea of the strength of the different types of forces that are present.